When we started the second half of calculus, I mentioned that it was called integration, and that is because it involves evaluating something called an integral. So our job today is to connect what we've been doing with approximation to the concept of what an integral is. I will tell you up front that it's a lot of terminology and notation that we have to get through, but that's going to build the connection that we need to move forward with evaluating integrals. So if you would copy the learning target with me, it's to interpret the definite integral as the limit of a Riemann sum. I'd like to start by defining what a Riemann sum is, and it's just an expression of the rectangular approximation method that we've been working on, but it does it in a formal way using summation notation. So let's take a look at this hypothetical graph, an increasing function. We happen to have a left rectangular approximation, and we've got our heights along the x-axis, and our b1, b2, and b3 are our y values. We're just going to be looking at that as we talk about how the rectangular approximation method becomes the summation notation. So we're going to transition from what we've been looking at to a little more formal notation. So this first line, your A equals BH plus BH, that is your expression for your RAM. And in the second line, I hope that you could see, since all the H's were the same, it's just factored out as a GCF. And in the third line, you can see that the H actually gets substituted by delta X. And that's really just a notation switch. And this is where the graph is going to help us understand how all this substitution is taking place. I think you can agree that the height of each rectangle is just a change in the X value on the x-axis. And in the third to fourth line, you're going to see that all the bases have been replaced with function values, which of course are just y values. And again, we can see that pretty readily on the graph, that each of those bases would be a function value of the graph at those x values. So you can see that what we have in the parentheses is a sum of function values. And mathematically, you probably have seen this symbol before. It's a Greek letter called sigma, and it represents a sum. And it basically takes a long sum and condenses it so you don't have to write such a long expression. So when we go down from this fourth line to the fifth, you're going to see that the delta X is still present. But the sigma is representing that we have a sum of all of these f of x values. So it basically just packs it into a nice condensed notation. So if you just want to make a note, that sigma literally means sum. So the resulting expression here with the sigma is what we call the Riemann sum. And it's important to realize that both the RAM approximation and the Riemann sum are both approximations, because as we'll be seeing very shortly, our ultimate goal is to get the actual area instead of just an approximation. So as mathematicians started to think about how can we get the exact area instead of just an approximation, they began to realize that if you started making the heights of your rectangles smaller and smaller, that the rectangles would fit closer and closer to the function until virtually you had no space left, and it would give you the exact area under the function. And theoretically, the only way to do that was actually to use an infinite number of rectangles. That would give you the exact area. So what you're going to see in front of this next expression is we now have a limit as n goes to infinity. So that's saying the number of your rectangles is going to infinity. So we've got this expression that's mathematically correct, and it expresses the infinite number of rectangles, finding the exact area. But you might agree it's a little bit bulky. It's got a lot of subscripts, some deltas. I always say it's kind of physics-like and complicated. So mathematicians decided to clean it up and make it a little bit prettier. So what they decided to do was to express a Riemann sum with limit to infinity. They chose the integral symbol. So this is what we are talking about when we say an integral. And you may have seen it before, maybe not, but it's actually a symbol from the Roman letters, which is interesting since sigma is Greek, and it also means sum. And I find that easy to remember because it's basically an elongated S. Although at first glance these two expressions look a lot different, let's go ahead and figure out what goes where and how they translate to be the same expression. So what happens with the limit to infinity and the sigma is that those two get replaced by the integral symbol itself. So when you see the integral symbol, it is implied and understood that the limit of rectangles is going to infinity. It's an infinite limit. We can see a delta x, and I think you would figure out pretty quickly that dx represents that same concept. And lastly, we have the f of x. And instead of having the x sub k, they just dropped the subscript and made it f of x. So again, just cleaning it up, making it look a little more concise. And that is what we call the definite integral. The most important thing that we realize about the definite integral in contrast to the RAM and the Riemann sum is that it gives us the exact area as opposed to the approximation that the other two give us. And one last note about this delta x that turned into a dx, that is called the variable of integration. And almost all the time it's going to be the dx, but sometimes we'll see a different variable in place, and it's just basically telling us what variable is the integral using. Just to sum up all the translation with the notation that we've gone through, here's the main idea. The definite integral gives us the exact area between the function and the x-axis on the interval a to b. Now you might have noticed that our integral had an a and b attached to it, and those are called limits. It gives us the interval on which we're finding the area, and we call this the lower limit for a, and b is our upper limit. The good news for us is that now that we've made it through all of this terminology and notation, we can use the skills that we've already learned with RAM and trapezoidal sum, and they all can be used to approximate a definite integral. So we don't have the skills yet to find the exact area. We will pretty soon in the semester, but right now the best we can do with the skills we have is to use one of these approximation methods to approximate the definite integral. The first example asks us to use a left Riemann sum, which is just really a fancy way of saying an LRAM, with 3 equal subintervals to approximate the integral from 3 to 12 of this function s of t, which represents snowfall. So as soon as I see equal subintervals, I'm going to use my h equals b minus a over n. So subtract your time interval and divide it by, we want 3 equal subintervals. So that looks like 9 over 3, which would be 3 for our height. Since we're doing a left Riemann sum, we know not to use the last function value, so let's cross that out. And since we're approximating the integral, what we're going to do is actually copy that integral symbol, which is a big deal in your calculus life to draw your first integral. So we've got the integral of s of t dt from 3 to 12, and we are approximating, so use your squiggle. And now let's set up our left RAM. We know that the height is 3 for all of our rectangles, and the bases that we left to use are 1, 2, 3. So if we multiply and add, that's going to give us 18. We know that when we multiply our time by our function, the time units cancel out, so we're left with inches. And in the context of the problem, we're talking about how much snow fell on the interval of 3 to 12 hours. Lastly, we're asked about our approximation being greater than or less than the integral. So I attached a left rectangle to my increasing function y values. So it would be less than because s of t is increasing.